Welcome to WikiPodcast. Have you ever paused to consider if time truly marches on at the same relentless pace for every single one of us, no matter where we are or how fast we're moving? Or what about that ultimate cosmic speed limit? Is reaching the speed of light just a fantastical sci-fi dream? Or is there, a deep physical truth behind it? Today, we're embarking on a journey into one of the most profound and, frankly, mind-bending theories of modern physics, special relativity. It's a cornerstone that fundamentally reshaped our understanding of time, space, and the very nature of motion, revealing secrets that really challenge our everyday intuition.
Absolutely. And our mission for this deep dive is to unpack how a couple of surprisingly simple yet revolutionary assumptions about the universe lead to some truly astonishing consequences. We'll move beyond the familiar and explore how concepts you thought were absolute, like time and distance, can actually be quite, well, fluid. Get ready to truly challenge what you thought you knew about reality.
Okay, let's dive straight in then. Every groundbreaking theory has its foundational principles, right? And special relativity is no different. It rests on just two postulates that, while they seem straightforward, kind of unleash this cascade of incredible implications. Can you walk us through what these two pillars are and maybe why they were such a radical departure from classical physics?
Sure, happy to. The first postulate is the principle of relativity. It essentially states that the laws of physics are the same for all observers who are moving uniformly what we physicists call inertial frames of reference.
Inertial frame. So, like, not accelerating.
Exactly. Think about it. If you're on a smoothly moving train, no bumps, no acceleration, and you drop a ball, it falls straight down, just like it would if you were standing still on the ground. The laws governing its fall don't change just because you're in motion.
Okay, that seems fairly intuitive, actually.
It might seem obvious now, yeah, but formally stating it is crucial. Now, the second postulate is where things get really revolutionary: the constancy of the speed of light. This asserts that the speed of light in a vacuum is not only the universe's ultimate speed limit, but it's also measured to be the exact same speed.
The exact same.
The exact same speed for all observers, regardless of how fast the light source or the observer themselves are moving.
Whoa. Okay, that definitely doesn't feel intuitive.
Not at all. It shattered classical notions. Before Einstein, physicists, they mostly thought light traveled through a fixed medium called the luminiferous ether, like waves through water.
Ether, right, I've heard of that.
But pivotal experiments, like the famous Michelson-Morley experiment back in 1887, tried to detect this ether wind and found nothing.
Zilch.
So no ether.
Exactly. It left this huge void in physics. Einstein's postulate elegantly filled that void, but it forced a complete rethink of space and time themselves. Okay, so if the speed of light is this absolute, unyielding constant for everyone, then yeah, it feels like our everyday ideas about how time and space work together must be completely thrown out. How do physicists even begin to describe things like events and measurements in this new relativistic universe?
That's a really crucial point. We have to be precise. So when we talk about an event in relativity, we mean something happening at a very specific point in space-time.
Space-time, not just space and time.
We'll get to that. But yeah, an event is a specific location and a specific time, like a lightning strike hitting that particular tree at exactly 3:15 p.m.
Got it. Place and time.
And clocks in relativity aren't just wristwatches. They're any consistent periodic device we use to mark the passage of time. Could be an atomic clock, could be anything that ticks regularly. What's truly mind-bending is that even though an event happens, different observers who are moving relative to each other might actually disagree on when or where that event occurred.
They disagree.
Mm-hmm.
Seriously.
Seriously. Unless it happens right at their location at the same time, otherwise their measurements can differ.
Okay, here's where I think it gets really fascinating.
Yeah.
You mentioned space-time. Special relativity doesn't just treat space and time as separate things, does it?
Yeah.
It actually weaves them together into this unified four-dimensional fabric called space-time. That seems like a massive shift.
It is a massive shift.
Yeah.
Precisely. Space-time is the physical union of the three dimensions of space we know: length, width, height, and one dimension of time. And a key concept here is the space-time interval between two events. Think of it like a sort of generalized distance, but measured through this four-dimensional space-time.
A distance in space-time.
Kind of. And what's incredible is that this interval, the space-time distance, remains the same for all observers, no matter how they're moving relative to each other.
Wait, so distances in space can change and durations in time can change, depending on who's looking.
Exactly.
But this space-time interval thing stays constant.
That's it. It's an invariant, a true constant of reality. It really shows how deeply intertwined space and time are. They aren't separate. They're two aspects of a single entity, space-time.
Wow. Okay. So going back to that constant speed of light, if it's the same for everyone, what does that do to our idea of events happening at the same time? My common sense tells me if two things happen simultaneously for me, they should happen simultaneously for you, right? What's wrong with that?
That common sense assumption is one of the first casualties of special relativity. This leads to what's called the relativity of simultaneity.
Relativity is simultaneity.
Yeah. It means that two events that appear simultaneous to one observer might not be simultaneous to another observer who is moving relative to the first one.
Can you give an example?
Sure. The classic one is a train. Imagine lightning strikes both ends of a moving train car simultaneously. An observer standing exactly in the middle of the train car might see the light flashes from both strikes reach them at the exact same moment. So for them, the strikes were simultaneous.
Okay, makes sense so far.
But now consider an observer standing still on the ground, watching the train go past. Because the train is moving, the observer on the ground will actually see the light from the lightning strike at the front of the train reach them before the light from the strike at the back.
Before. Why?
Because the front of the train is moving towards where that observer will be when the light arrives, while the back is moving away. Since the speed of light is constant, the light paths have different effective lengths relative to the ground observer. So for the ground observer, the strikes were not simultaneous. The one at the front happened first.
Whoa. Okay, that messes with my head a bit. So simultaneity isn't absolute.
It's not absolute. The only exception is if two events happen at the exact same location and are simultaneous in one frame, then they'll be simultaneous in all frames. Otherwise, it depends on your motion.
Which completely overturns that idea of a universal now that everyone shares.
Precisely. There's no absolute present moment shared across the universe. Your now depends on your frame of reference.
Okay, let's unpack the next mind-bending effect then, time dilation. If simultaneity is relative, what happens to the actual flow of time when things start moving really, really fast, like close to light speed?
Time dilation means exactly what it sounds like. Time stretches. If a clock is moving relative to you, you will observe that clock running genuinely slower than an identical clock that is stationary relative to you.
Slower, like actually ticking slower.
Actually ticking slower. And this isn't some trick of perception or an optical illusion because of light travel time delays. It's a measurable physical effect on the rate at which time itself passes for that moving clock, from your perspective.
Is there real-world proof of this? It sounds like science fiction.
Oh, absolutely. A classic real-world example involves particles called muons. These are subatomic particles created when cosmic rays hit our upper atmosphere. When we create muons stationary in a lab, they have a very, very short lifespan. They decay incredibly quickly. But the muons created high up in the atmosphere are traveling towards Earth at near light speed. Because they're moving so fast relative to us, their internal clocks run much slower from our perspective.
Ah, so time dilation kicks in.
Exactly. Their lifespan, from our point of view, gets stretched out so much that many more of them survive the journey down to the Earth's surface than classical physics would predict. We detect them down here. It's direct proof.
Wow. Okay, that's compelling. I remember hearing about a thought experiment that helps visualize this, the light clock. Can you walk us through that?
Yes, the light clock thought experiment is a really elegant way to understand why time dilation happens. Imagine a very simple clock. It consists of two parallel mirrors and a pulse of light bouncing vertically between them. Each round trip up and down is one tick of the clock.
Okay, simple enough.
Now, for an observer who is stationary with this clock, the light pulse just travels straight up and straight down. Let's say that distance is L. The time for one tick is just the total distance, 2L, divided by the speed of light, c.
Right. Distance over speed.
But now, let's imagine you are moving rapidly past this clock, perpendicular to the direction the light is bouncing. From your perspective, the mirrors are moving horizontally. So, as the light pulse travels from the bottom mirror to the top one, the top mirror has moved sideways, and as it travels back down, the bottom mirror has moved further sideways.
Ah, so the light isn't going straight up and down anymore from my view.
Exactly. From your moving perspective, the light pulse travels along a longer, diagonal zigzag path.
Okay, I can picture that. A longer path.
And here's the key. Einstein's second postulate says the speed of light, c, is absolutely constant for all observers. It's the same for you as it is for the person stationary with the clock. So if the light is traveling at the same constant speed, c, but it has to cover a longer zigzag distance from your perspective.
It must take more time.
Precisely. It simply must take longer for you to observe one tick of that moving clock compared to the observer stationary with it. That longer duration is time dilation. Moving clocks run slow.
That actually makes a strange kind of sense when you put it that way.
Yeah.
Okay, so time stretches. If time can stretch and bend, what about space? Does distance change too? Is that another layer we need to wrap our heads around?
Indeed it is. Space is equally affected, and it's intrinsically linked to time dilation through the constant speed of light. Objects moving at very high speeds appear shorter or contracted in the direction of their motion. This effect is known as length contraction.
Length contraction. So things literally shrink.
They appear shorter in the direction of motion when measured by an observer relative to whom they are moving fast. Again, like time dilation, this is a genuine, measurable physical effect on the actual measured distances, not just a visual trick or perspective distortion.
So if I were flying past, say, a spaceship at near light speed,
From your perspective, that spaceship would appear shorter along its length, the direction it's moving relative to you, than it would appear to someone riding on the spaceship. Its height and width wouldn't change, just the length and the direction of motion.
okay, shorter in the direction of motion, got it. Time dilation, length contraction, these effects are real.
Very real and deeply interconnected. You can't have one without the other if the speed of light is constant for everyone.
This leads us perfectly into one of the most famous and seemingly contradictory thought experiments. The twin paradox. It sounds like a riddle, right? One twin takes off in a spaceship, travels near light speed to a distant star, turns around, comes back. When they land, they've aged less than their twin who stayed on Earth. How is that not a paradox? Doesn't relativity say motion is relative? Couldn't the traveling twin argue the Earth twin was the one moving and their clock should be slower?
That's the crux of the apparent paradox, but it dissolves when you look closely because the situation is fundamentally asymmetrical.
Asymmetrical, how so?
The key is acceleration. The traveling twin cannot complete their journey without accelerating. They have to accelerate away from Earth, decelerate to stop at the distant star, accelerate again to come back, and finally decelerate to land on Earth.
Oh, acceleration. The stay-at-home twin doesn't do that.
Exactly. The Earth-bound twin remains in a single inertial frame of reference, or at least much closer to one than the traveling twin. The traveling twin, however, changes reference frames multiple times due to acceleration and deceleration. This breaking of symmetry is crucial. Acceleration is not relative in special relativity in the same way uniform velocity is. All observers agree on who accelerated.
So the acceleration makes their experiences fundamentally different.
Yes. Because of the acceleration and the different path taken through space-time, the traveling twin experiences less proper time. Proper time is the time measured by a clock moving along with the observer. Their journey through the four dimensions of space-time is literally shorter in terms of elapsed proper time, so they genuinely age less. It's not a paradox, but a direct consequence of how space-time geometry works.
Wow. Okay, the asymmetry from acceleration is the key. That clears it up. So we often hear the phrase, nothing can travel faster than light. How does special relativity actually confirm this? What mathematically stops something from breaking that barrier?
This comes directly from the Lorentz transformations. These are the equations that correctly describe how measurements of space, time, mass, and energy change when you switch between different inertial frames, replacing the old, incorrect Galilean transformations.
Lorentz transformations, okay.
These equations show that as an object with mass gets closer and closer to the speed of light, its relativistic mass increases.
Its mass increases.
Yes. From the perspective of a stationary observer, it effectively becomes harder and harder to accelerate it further. As it approaches the speed of light, its relativistic mass approaches infinity.
Infinity. So you'd need infinite energy to reach light speed.
Precisely. You'd need an infinite amount of energy to accelerate an object with mass to the speed of light, let alone beyond it. So c acts as an insurmountable speed limit for anything with mass.
And what about time at that speed?
The Lorentz transformations also show that time dilation becomes infinite at the speed of light. Time would essentially stop for an object traveling at c relative to an external observer.
Okay, so infinite mass, time stops. Seems like a pretty firm barrier.
It is, and there's another reason. Causality. If you could send signals or objects faster than light, the equations show it would be possible to send a message into your own past.
Send a message to the past. Like Breaking causality.
Exactly. You could create paradoxes to tell yourself not to send the message, for instance. Physics, as we understand it, doesn't allow for these causal loops. The speed of light limit preserves the cause and effect structure of the universe.
That's fascinating. But you mentioned something earlier. Despite this limit, time dilation allows for incredible space travel possibilities.
Yes, this is one of the most mind-boggling implications. While you can't exceed c, time dilation works in the traveler's favor. Imagine a spaceship that could accelerate constantly at 1g that's the same acceleration as Earth's gravity, so it would feel comfortable for the astronauts.
Okay, constant 1g acceleration.
Due to time dilation, the astronauts' clocks would run much, much slower relative to Earth as they approach light speed. So they could theoretically travel vast interstellar distances within their own lifetimes. For instance, reaching the Andromeda Galaxy, which is over 2 million light years away.
2 million light years. That sounds impossible.
It would take just about 28 years of ship time, of the astronauts' own experience time, if they maintained that 1g acceleration, slipping halfway to decelerate.
Only 28 years for them.
But back on Earth, because Earth's clock wasn't dilated nearly as much, over 2 million years would have passed.
That is absolutely staggering. The difference in experience time.
It highlights just how flexible time really is under relativity. The speed limit is absolute, but the experience of time is relative.
Wow. Okay. And this brings us inevitably to perhaps the most famous equation in all of science, EMCCP washouts. How does that fit into this picture of special relativity?
EMCC is arguably the most profound consequence of special relativity. It's Einstein's derivation of mass-energy equivalence. It fundamentally shows that mass and energy are not separate things, but are actually two different forms of the same fundamental stuff. Mass is an incredibly concentrated form of energy.
Mass is energy, and energy has mass.
Essentially, yes, E is energy, m is mass, and c is the speed of light. Since c is a huge number, c squared is enormous. This tells you that even a tiny amount of mass contains a vast amount of locked-up energy.
Like in nuclear reactions.
Exactly. Nuclear fission and fusion release energy by converting a tiny fraction of the mass of atomic nuclei directly into energy, according to Imam-Sivesva. It also means that adding energy to a system, like heating it up or making it move faster, actually increases its mass slightly, its inertia.
So it wasn't just pulled out of thin air. It comes directly from the principles of relativity.
It's a direct mathematical consequence of the postulates of special relativity, particularly how energy and momentum transform between different reference frames. It shows that inertial mass is essentially a reserve of energy.
Amazing. Now, visualizing all this space-time, relative simultaneity, light cones seems really difficult. You mentioned physicists use space-time diagrams or Minkowski diagrams. How do those help?
They are incredibly helpful tools, yeah. They basically draw space-time. Usually you draw one space dimension horizontally and the time dimension vertically.
Space and time on one graph.
Right. And the crucial thing is how light is represented. Because the speed of light c is constant, light rays traveling in any direction are always drawn as lines at 45 degrees on these diagrams, if you choose your units correctly.
45 degrees always means light speed.
Yes. This gives a fixed structure. Then you can plot events as points on the diagram. The path of an object through spacetime is called its world line. These diagrams let you visualize things like time dilation and length contraction geometrically. You can see how the now line, the line of simultaneity, tilts for different observers.
And the light cone.
Ah, yes, the light cone is fundamental. From any event, a point on the diagram, you can draw the 45-degree lines representing light traveling outwards into the future and inwards from the past. These lines form two cones, the future light cone and the past light cone.
What do they represent?
The future light cone contains all events that can be influenced by the event at the vertex. The past light cone contains all events that could have influenced the event at the vertex. Anything outside the light cones is causally disconnected. It can't affect and cannot be affected by the event at the vertex because that would require faster than light travel.
So it visualizes causality.
Precisely. It gives a clear geometric picture of the causal structure of spacetime according to relativity.
And I think you mentioned four vectors as well for a deeper mathematical approach.
Right. For doing calculations more formally, physicists use mathematical objects called four vectors. Think of them as packaging space and time components together. For example, instead of just position in 3D space, you have a space-time position four vector that includes time as its zeroth component.
So it combines space and time mathematically.
Exactly. There's also a four velocity, a four momentum, which combines energy and regular momentum. and even a 4 force. The beauty of these 4 vectors is that the laws of physics, when written using them, automatically look the same in all inertial reference frames. They respect the principle of relativity inherently. It makes the math much more elegant and powerful.
It sounds like a very efficient way to handle the physics.
It is. It captures the underlying unity of space-time.
Now, there's a common misconception I wanted to touch on. People often think special relativity only applies to objects moving at constant velocity. That if something accelerates, you immediately need general relativity. Is that true?
That's a very common misunderstanding, but no, it's not true. Special relativity can handle acceleration perfectly well.
It can. So what's the distinction with general relativity then?
The key distinction lies in gravity and the nature of acceleration. In special relativity, we're usually working in flat spacetime, no significant gravity, and acceleration is considered absolute. All observers agree that an object is accelerating. General relativity is Einstein's theory of gravity. It describes gravity not as a force, but as the curvature of spacetime caused by mass and energy. In GR, all motion, including acceleration and free fall under gravity, becomes relative, viewed as objects following the straightest possible paths, geodesics, through curved spacetime.
So SR handles acceleration in flat spacetime, GR handles gravity and curved spacetime, which affects acceleration too.
You've got it. So you can analyze accelerating rockets, charged particles and electric fields, and so on, using only special relativity as long as gravity isn't the dominant factor.
Is there a good thought experiment showing acceleration in SR?
Yes, a classic one is Bell's spaceship paradox. Imagine 2 spaceships, initially at rest side by side, connected by a fragile string. Then, they both start accelerating identically at the same moment, as measured in their initial rest frame, maintaining the same acceleration profile.
Okay, accelerating identically, so the distance between them should stay the same, right? The string should be fine.
That's the classical intuition. But in relativity, it's trickier. Because of length contraction from the perspective of the initial rest frame, the fixed physical distance between points on the accelerating ships must shrink. However, the ships are programmed to accelerate identically in that rest frame. But consider the frame of the leading ship. Due to the relativity of simultaneity, it sees the rear ship starting to accelerate slightly later than it did. Furthermore, due to length contraction of the space between them in their moving frame, the proper distance required to maintain formation increases.
The distance between them increases in their own accelerating frame.
Effectively, yes. The requirement to maintain identical acceleration as measured in the initial frame leads to an increasing proper distance between them in their own frame. The string, trying to maintain a fixed proper length, experiences increasing tension and eventually snaps.
Wow, that's incredibly counterintuitive. The string breaks even though they accelerate identically in the starting frame.
It's a striking example of how relativistic effects, especially length contraction and the relativity of simultaneity, play out even with acceleration. Another interesting concept is the idea of an apparent event horizon for a uniformly accelerating observer, a boundary beyond which light signals can never reach them.
An event horizon just from accelerating.
Oh,
Wild. This has been a truly mind-expanding journey through special relativity. It's just incredible how these seemingly abstract concepts, born from thought experiments, have been so rigorously proven by real-world observations over the last century.
indeed. And the evidence started accumulating even before Einstein's 1905 papers, although its significance wasn't fully grasped then. Like the Fizeau experiment way back in 1851, measuring the speed of light in moving water. The results didn't quite fit classical ideas, but were perfectly consistent with the relativistic way velocities add.
So hints were already there.
Hints were there. But of course, the pivotal one was Michelson-Morley in 1887. Their failure to detect the ether wasn't just a null result, it was a profoundly important result. It basically screamed that the speed of light doesn't depend on the observer's motion relative to any supposed medium.
It directly paved the way for Einstein's second postulate.
Absolutely. It was a cornerstone piece of experimental evidence, even if interpreting it took time. And today, these effects are not just historical footnotes or theoretical curiosities. The relativistic Doppler effect, how the frequency and color of light changes due to relative motion, is used constantly in astrophysics. It's how we measure the expansion of the universe, the rotation of galaxies, the speeds of stars.
So a working tool for astronomers.
A fundamental tool. And maybe the most relatable example is something many of us use every day: GPS.
GPS relies on relativity. How?
Yes, both special and general relativity are crucial for GPS accuracy. The satellites are orbiting Earth very fast, that's special relativity's time dilation, making their clocks run slightly slower than clocks on Earth. But they are also in a weaker gravitational field than we are on the surface. That's general relativity's effect, which makes their clocks run slightly faster.
Ah, so both effects are at play.
Exactly. And engineers have to precisely calculate and correct for both of these relativistic time effects. If they didn't, the timing errors would accumulate so rapidly that your GPS position would be off by several kilometers within just one day.
Kilometers a day. Wow, that would make it useless.
Completely useless. So every time you use GPS, you're relying on the fact that Einstein's theories of relativity are incredibly accurate descriptions of reality. It's a daily practical confirmation.
That's an amazing tangible example. Okay, as we wrap up this deep dive, what stands out to you as the single most profound takeaway from special relativity, something you hope our listeners really carry with them?
Hmm. The most profound takeaway, I think for me, it's the fundamental shift in understanding time. The realization that time isn't this absolute universal metronome ticking away identically for everyone everywhere. Instead, time is personal, it's relative, it's interwoven with space, and its passage literally depends on your motion through space-time. Your clock's rate is unique to your world line.
Time is personal.
Yeah, and that opens up just incredible questions, doesn't it? If time and space are so fluid, so interconnected, what does that truly imply about our perception of now? What does it mean for the fundamental fabric of reality itself? It forces you to reconsider the very nature of existence.
A truly deep thought to end on. It definitely makes you reconsider everything you thought you knew about time. Thanks for listening. Write us your opinion in the comments on how your understanding of time might change now. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.